This is a math review of the Chapter 2 Radiation Concepts math problems that we discussed. I'm going to work a few of these problems just so you can get a basic understanding. Their key should be available to you, as well as extra practice problems and the key that goes with that. So the first thing we talked about was the 2n squared, which determined the maximum number of electrons allowed in a specific shell. We worked this one in the presentation, so I'm going to jump down to number 2. So, this says, what is the maximum number of electrons allowed in the p shell of an atom? So, K is 1, L is 2, M is 3, N is 4, O is 5, and P is going to be 6. So that's the 6 shell. So, we should have 2, 6 squared. So, first, by order of operations, we have to do 6 squared. 36 times 2, and that equals 72. So your answer is the maximum number of electrons allowed in the p shell of an atom is 72. Okay. Half-life. Remember, half-life measured radioactive decay. So let's look at this first problem. Given an 80 microcurie sample of iodine with a half-life of 6 days, the radioactivity will be 5 microcuries in how many days? So, let's start by writing 80 at the top. So after 6 days, so 6 days have passed, we're going to now have 40 microcuries. Okay, after another 6 days, we're going to have 20 microcuries. Remember, we have to get all the way down to 5. So another 6 days have passed, we're down to 10. And then another 6 days have passed, we are now at 5. So it's asking how many days have passed. So 6 times plus 6 plus 6 plus 6, or 6 times 4, is going to be 24. So your answer is 24 days. So pretty much you're just halving it. Every time you half the sample, you're taking into consideration that half-life. Whether the half-life is 6 days, your half-life could be in hours. Just make sure you answer in the correct unit. Let's work one more half-life problem. Sometimes it'll ask you to determine how much time has passed, or how much iodine is going to remain after so many days. So it can ask it both ways. So here's kind of an opposite one. So if the half-life of iodine is 4 days, approximately how much iodine remains of an original shipment of 50 microcuries in 20 days? So original shipment is 50 microcuries. After 4 days have passed, we're going to have 25. After another 4 days, we'll have 12.5. Remember, we're wanting to know how much in 20 days. After 4 more days, we have 6.25. After another 4 days, so now we're at 16 days, we're at 3.125. And then finally, after 20 days, because 1, 2, 3, 4, 5, you should have 1.5625, or you can round that to 1.56 microcuries. And make sure you include, in any math problems that you do, make sure you include the unit at the end. And whenever you are doing math on a test, always circle your answer so that the person grading your test knows exactly what your final answer was. The wave equation is velocity equals frequency times wavelength. What is the frequency of a photon with a wavelength of 200,000 meters? First, recognize that the problem is asking for frequency. I have this triangle right here. This helps a lot of people, and you can use it for several formulas that we'll be talking about in chapter 3 moving forward. Because sometimes you won't always be multiplying. You might end up dividing. So again, what is the frequency of a photon? So we're looking for frequency. So cover frequency up. Frequency is going to equal velocity divided by wavelength, because the C is now falling over the wavelength. Now, if we were looking for C, you would do frequency times wavelength. Okay? If it was asking what is the wavelength, cover up wavelength, it would be velocity divided by frequency. So this may help you. It's just another tool. So, how we set this up. And again, if you notice, I'm using F instead of V for frequency because it's just a little bit easier to look at. So, our equation is going to start with frequency equals velocity over wavelength. And now we plug in our numbers. Frequency equals velocity, which is 3 times 10 to the 8th. Again, that never changes. Over 200,000 meters is the wavelength. Now, if you notice, this isn't going to work because you can't use scientific notation in a regular number. So we've either got to take 3 times 10 to the 8th out of scientific notation or put 200,000 into scientific notation. So once you do that, so we're going to put 200,000 into scientific notation. So 3 times 10 to the 8th divided by 2, because you can never have any more than 2 digits times 10 to the 8th or whatever your 10 exponent is. You can never have 2 numbers, so we can't do 20, we can only do 2. You can never do 0, so only 1 through 9 whenever you're doing scientific notation. So 2, and let's see how many places we had to move. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, because there's 5 zeros. It's a positive number, so it's going to be 2 times 10 raised to the 5th. So now we can actually work this problem. So now, when you're dividing versus multiplying, the rules are a little bit different. In this case, we're dividing, so you're going to do 3 divided by 2, which equals 1.5. So that's the first step. We're doing still in scientific notation, so you're going to do times 10. And now we got to figure out the exponent. You aren't going to divide the exponents. When you're dividing scientific notation, you're going to subtract the exponents. So 8 minus 5 is 3. Okay. Now this answer should have hertz at the end because frequency is measured in hertz. So the 1.5 times 10 to the 3rd hertz is your final answer. If you want, you can also answer as 1,500 because that is 1.5 times 10 to the 3rd taken out of scientific notation. Now it's asking what kind of energy is it. If you look at your electromagnetic spectrum chart from your presentation, if you look at the electromagnetic spectrum chart from your chart, 10 to the 3rd right here, right here on frequency, it kind of falls really close to radio waves, but primarily this is going to be heat radiation. So either answer is fine. I like going by this chart a little bit better for these problems specifically. So 10 to the 3rd under frequency, it is heat, is the type of energy. Okay, let's work another one. So this one says, what is the wavelength of a photon with a frequency of 2.34 times 10 to the 20th hertz? So wavelength is going to be velocity over frequency. So when we plug everything in, wavelength equals 3 times 10 to the 8th, because remember that never changes, divided by 2.34 times 10 to the 20th hertz. So now we can do 3 divided by 2.34, and you can round that 2 decimal places. So that is going to give us 1.28, because remember we can't do more than a single digit 1 through 9 in the beginning of our scientific notation, times 10. Remember we're dividing, so we have to subtract the exponents. So 8 minus 20 gives us -12. And this is measured in meters. So don't forget your meters. Now when you put this in out of scientific notation, you get a really long number, 0.00000000128. So you can leave it in scientific notation. Now what kind of energy is it? So let's hop back over to our electromagnetic spectrum. 10 to -12. If you drop straight down from wavelength, okay, you hit gamma and you hit higher end of X-rays. So you can put gamma and X-rays as your answer. The next problem is asking, what is the frequency of a 72 keV X-ray photon? So this is Planck's theory. Planck's theory equals energy equals Planck's constant times frequency. You can also use the triangle for this like we did for the wave equation. You'd put E at the top, H on the lower left side, and frequency on the lower right side. Since this is asking for frequency, frequency is going to equal energy over Planck's constant. However, the first thing we have to do, if you notice, 72 kiloelectron volts needs to be changed to just electron volts. We can't do kiloelectron volts when everything is measured in electron volts. So when we change this, if you remember, look at your numeric prefixes worksheet, you might have heard King Henry died Monday drinking chocolate milk. Now, kiloelectron volts, K right here, we're going to move our decimal place over 1, 2, 3, because electron volts is just our unit, and this M in the middle just stands for the actual unit, which is electron volts. So kiloelectron volts, 1, 2, 3. So that means we're going to add 3 spaces. Okay. So now we just went from 72 kiloelectron volts to 72,000 electron volts. Now we can go ahead and work our problem. So frequency equals our energy, which we have to put in scientific notation, which is 7.2 times 10 to, and then we got to count the spaces, 1, 2, 3, 4. We have a positive number, so that's going to be 10 to the 4th. And then we are going to divide it by Planck's constant, which is 4.15 times 10 to the -15th. Since we're dividing, you're going to do 7.2 divided by 4.15, which is going to equal, rounding to 2 decimal places, 1.73 times 10. Now we got to figure out the exponent. 4 minus -15 if you remember working your negatives, that kind of turns into a plus positive. So 4 minus negative 15 is going to give you 19. And this is going to be your final answer. And your unit, since we're looking for frequency, should be